Okay, class, continuing on Whitlock and Schluter Chapter 13 here. We want to look at approaches to dealing with non-normality. So you run your Shapiro-Wilk test, you get a low p-value, you're not normal. What do? According to the book, there's three options: ignore, transform, or use a non-parametric method. So when would you ignore it? You would be able to ignore the violation when the data are, when the test is robust. When you're using a robust test, okay, what's a robust test? Okay, a test is robust if the data are not too far off from normal, then the test results will still be valid. So a test is robust when results are still valid under mild assumption violations. Okay. Now, as an example, if I go up to our previous couple of cases here, this case A passes, so everything's fine. So that's okay. B, this one violates, so we're not okay, but it's just some points in the tails. Otherwise, it's looking pretty good. So this one is going to be not too bad. We could still use the normality assumption even with this data if it's a robust test. C and D, those are just no. We're not even close. Okay, it's better determined from a normal QQ plot than from a Shapiro-Wilk test on this robustness. It's a matter of the craft and identifying through experience than it is of giving you some number on a Shapiro-Wilk test. Okay, number two, transform the data. All right, so if the violation is not mild or you're not using a robust test, then we're going to transform the data. Transformations are here. Transformations. And let me just go right into R to demonstrate a transformation. I'm going to use the, this is the Whitlock-Schluter text examples file, and we're going to use, make sure to attach your data, the Marine Reserve example. It's page 324 in the text. So I'm just going to declare X to be the biomass ratio, just to make the scripts easy to read. And then I'm going to run a histogram of X. Here's the histogram. It's got a nice peak, but it's very skewed right. So what's the QQ plot look like? Ooh, you can see we don't have a good line there. Nevertheless, is it close enough? Let's check Shapiro-Wilk. So I'm going to run the Shapiro-Wilk test, and we'll see that's a pretty low p-value. So these data are not normally distributed, not even close. Here's where the log transformation comes in. I want to just look at the data X, and there it is. Kind of hard to see a good grip on it. If you just do a sort of X, that at least helps. We can see that skew rightness coming in. Most things are in the ones, but you've got a few in the twos. So that's what's making it go way skew right. What is a log transformation? Log transformation means that we take a logarithm of all the observations. So I'm just going to do it. Let's do ln x equals log x. This is the natural log, by the way. Okay, so let's look at sort ln x, and you can see those values are much, much smaller. What does their histogram look like? It's still skewed right, but things have tightened and it doesn't look as extreme. So how does the QQ plot compare? Let's run that. QQ norm command. Ooh, closer to the line. And let's do Shapiro-Wilk. 0.06. We're above the technical 5%. We can freely not reject the null and go, these data are close enough to normal that they pass assumption. Then you can go ahead and run your test. We'll just do a t-test command. And I'm doing the t-test on the transformed data. I get a p-value. We reject the null hypothesis of the mean being equal to 0. And I'm not interested in the specific application, so won't worry about that. But the idea is you could use that. The confidence interval we'd want to adjust, but that's what we've got. Okay, so that's one. Let's go to the second one. Transforming the data. If we don't transform, maybe you tried to transform and you're not able to get normality still, we want to do a non-parametric method. Now the book gives a fair bit of detail about the non-parametric methods, and we may go into some of that detail in class. Here's what I want you to know now. Okay? For every parametric method we've done, and what's the difference between non-parametric and parametric? Okay, parametric has distributional assumptions. So let's just put that here. Distributional assumptions. Non-parametric attempts to avoid distributional assumptions. So avoid distributional assumptions. Okay. What does that mean? Well, you notice that we have an assumption of normality for those t-tests. That's a parametric assumption. If you violate that, then there have been tests that are developed which don't make that assumption. And there's different tests for different things, and it's not helpful to get into lots and lots of detail. So what I want to do is just say, for the one sample t-test, there's a thing called the Wilcoxon signed rank test. The book does signed test. Signed rank is better, so we'll just jump to that right away. For the two sample paired t-test, we can use Wilcoxon signed rank test. And then for the two sample independent t-test, we can use the Mann-Whitney-Wilcoxon test. Mann-Whitney and Wilcoxon both came up with the same thing at the same time. They just published different papers and had different notation, but it's the same underlying test. All those are inside of the Wilcox.test function in R, and so that's the one that we really need. There are some assumptions. Basically, we assume the data is randomly sampled, which we do on the parametrics as well, and then a symmetric distribution for these first two. The two sample independent, we just need same shape. It doesn't have to be symmetric. Okay, so that being the case then, let's just illustrate what it looks like in R. In practice, let's go to it here. Let's take example 13.4. This is page 334 to 337. And it looks like we need this data with these clades. And I'm not going to get into the specific interpretation here because I'm focusing in on just the stats part. So let's attach it and get to it here. Okay, so I'm going to call x1 and x2 the two different groups, and then we'll run this Wilcox.tests command. Okay, there it is. It says alternative equals two-sided. You could do a one-sided. You would use, I believe, greater or lesser. And this is a paired design, so I'm putting the paired equals true argument in. Again, if it was independent, then you dump that. So the syntax is relatively simple. What does it mean? Okay, tells me the data. The V is the test statistic. Again, we're not going to compute it by hand. We don't need to know details on it. what we want is this p-value. Okay, it's a 0.07, therefore it's bigger than our 0.05, so we will not reject the null hypothesis, and we'll go ahead and assume the null. What are the hypotheses? Okay, the null hypotheses, they're analogous to the hypothesis for the parametric cases. So the null hypothesis for the one sample was mu equals some constant, so I'll just put mu star, whatever the constant was. Two sample pair T, that one is typically mu diff equals 0. And the two sample independent T is mu1 minus mu2 equals 0. Key thing to know, for non-parametric tests, we use median instead of mean. And that covers what I need for my non-parametric test. So over here, it calls it a location shift. Technically it's median. People tend to think mean. It uses the term location shift, center, same thing. Okay, so we're not going to reject. We'll assume they're the same center. That covers it.